Do, 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 do. Hello, Outcross. Okay. Nice. I think I'm gonna go get something to drink real quick, and then we can start. Ba-da-ba-ba-ba-ba-ba-bum. Can you later do a calm time Radix tree? Um. Uh, so I think that it is technically possible to create a calm time Radix tree. Yes. I think right now it's not nice to do that at all. It requires you to bend everything a lot. And there is a proposal to add a comp time allocator. And once, assuming that the proposal works, you can't say for sure until it's really done. But once comp time allocator becomes a thing, then it should be possible to have a Radix 3 created at comp time. Yes. Honestly, in any case, I wouldn't worry about it too much because you always have one way of doing this type of work, which is not necessarily through comp time, but through the build system. So the way it works is that, let's say you have a list of words that you want to put in your Radix tree. And so what do you do is that you make a program that builds a Radix tree, a normal one, like a runtime. But what you do is that you invoke that program in your build pipeline, in your build script. And then the generated data structure at runtime, you basically save it as data, as binary data, and then you rehydrate it from memory. So you save it as binary data. You use you need to do some transformations to it because obviously you will need to adjust pointers. So basically you need to save it in a way where those pointers go from being pointers to kind of being, let's imagine, offsets in an array list, for example. So you don't point anymore at the next node at location something in memory, but you know that it's going to be the item number 1, 2, 3, 4, 5 in an array. So you need to apply those transformations. And there are serialization data formats that allow you to do that. And so you save that as a binary blob, and then you embed that binary blob in your final executable, and you rehydrate it at startup. So, which more or less that's kind of what a comp time Radix 3 would have to be otherwise, maybe with some caveats, not necessarily strictly the same way, but roughly speaking, it's the same thing. So these kind of shenanigans you can already pull off. That said, the point is, like, from a practical perspective. That said, I understand, that it's cool to say, oh, let's make a comp time Radix 3. Sure, that would be cool. But in any case, I would say it's much less useful than a runtime Radix tree. So that's what I'm starting with. Okay, let me go get something to drink, and then we can get started. In any case, Craglord, hello, good morning, afternoon for me, but still, I'll be right back. Hello. Hello, hello. Okay, I'm back. Hello, Jim. Hello, Rosashan. Hello, Andrew. Let's go. Okay, let's see if we can actually make some Radix 3 today. So let's take one last look at our tech. So our tech right now is, why does this look like this? This is our tech right now. We have a flexible array that you can put in a struct definition. That struct can also be packed, and we create a packed struct in turn, right? Yeah, we do put a nested packed struct, which is awesome, and we do that by default because it never hurts in our case. So yeah, flexible arrays, and then to those flexible arrays, you can give a this can be omitted because it's used as by default. Yeah, now you can do this. This is gonna be, by the way, this I'm going to copy and use in my Radix tree because that's a node. That's exactly the node definition that we're gonna use. I don't know. Maybe we're gonna, I don't know, change some things. We'll see. For example, I can already think of an improvement. Look at how we're doing is key 1 bit, is null 1 bit, and then we have 1 bit for this. I wonder what the combinations of all these things can be. Like, do we really need all of them? Can it be key and null, key not null? I don't know. Do we even need is null? We probably don't. Also, this definition is missing one last piece, which is the value. We're kind of forgetting about the value. Right. And where do we put the value? But in any case, we're going to see. So this is our stuff here. And I'm going to change this terminal to Zig Rax. And we have this main branch. Git status. There's a bunch of untracked files. We add git ignore. We add readme. We add license, but nothing else. We don't keep anything else. And then we do zig init, and check this out. We do a minimal init. And the problem is that even though it's a minimal init, it's adding the zig prefix, which fucking sucks. So we need to remove that. And we go back down, and then we do run init again, refusing to override, which is fair. But the problem is that if we do zig build, then it will complain about the fingerprint not being good. So we need to make a good fingerprint. Okay. And that works, and it doesn't do anything. It's just no ping, basically. Okay, that works. So mkdir source slash root.zig. This is going to be a library. Okay, we're going to put stuff in here. So we can create a separate node definition in another file. That works. But does it have to be this way? Maybe, maybe not. I'm trying to think a little bit if I want to split them or not. We don't really have a reason to split this. Although we can make a top level struct if we put node in another file. That maybe is not a bad idea. No, but we can't because it needs to be a packed struct. So definition has to go in here. So let's copy this. This is going to be our starting point. What's a flexible array? Good question indeed. So a flexible array, we need to go into our zone file. We need to add it as a dependency. Otherwise, paths above fingerprint. What? Okay, dependencies. Flex is gonna be dot path equals zig flex. That's it. Okay. So now, if we go here, we can do const. Actually, we need to go into the build script. All right, there's work to do actually. So const mod equals b dot create no, add module. Module's name is going to be let's call it Rax. Options are going to be root source file equals b dot path source slash root dot zig. I think we don't care about anything else, at least for now. Well, we want tests, I guess, at least, so that we can run tests on this. Problem is, we do need const target equals b dot standard target options const optimize equals b dot standard optimize option singular this time. And then we can do maybe something like this: const run tests. Or let's call it test step. And then test exe. So then we do test step dot depend on. Actually, it's the step dot step. I think. No, it's already a step. Never mind. Depend on ampersand b dot add run artifact, and we want to run test exe. And this is our testing stuff. And we're good. And we can add a failing test to make sure everything works. Although, wait, we're also missing one thing. Mod dot add import flex, and that's gonna be, we can do this const flex equals b dot dependency dependent name is gonna be flex arguments. We pass down nothing. We don't care. And then we do add import flex module flex. There we go. And actually we can even do it like this, I think. What's an import? It's name module, of course. I'm doing basically the same thing down below, just said in a different way. There you go, even more succinct. And this is, of course, like this. Okay, we did it. I don't think we're ever going to have other dependencies, so this should be it. So now it allows us to go into root and say const flex equals at import flex. And then we can say const flexible array equals flex dot flexible array. There we go. Let's add a failing test. Let's make a test that makes us sad. After std testing dot expect false. Don't have std. Good point. And now we should be sad because that test fails. There we go. Test fails. Actually, it's a slightly different problem. We need to do this. Now the test actually fails. Unexpected result because we expects true. It doesn't expect false. So this is where we're at right now. Okay, we have the super basics in place. This I'm not gonna call Rax node. I think I'm just gonna call node now because Rax is the entire project that we're in. Then we need the top level structure, which is the actual tree. So a tree probably it's either a pointer to the root node, and then we do everything through root nodes, through nodes. Technically, we could because this guy works this way, but it's probably not the greatest idea. So let's assume that there's going to be a root node. It's going to be a pointer to node. And maybe there's other properties that a Rax has. For example, should he keep a GPA? Maybe it should keep a GPA. Maybe it shouldn't. You know what? Let's not do that. Let's take a look at the C implementation. So what does the C implementation have? A bunch of debug stuff, which to be fair is not a bad idea. There's also Rax not found. Let's see, this is a special pointer that is guaranteed to never have the same value of a Radix 3 node, and it's used in order to report not found errors without requiring the function to have multiple return values. We'll see how we're going to do this in our case. We're probably not going to use this approach, although there's nothing wrong with it. Debug stuff. I guess what we care about is like starting Rax stack functions. Rax stack is a simple stack of pointers that is capable of switching from using a stack allocated array to dynamic heap once a given number of items are reached. This looks like a stack fallback allocator type of thing, except specific to what's happening here. It's used in order to retain the list of parent nodes while walking the Radix tree in order to implement set operations that need to navigate the tree upward. There we go. Hello. Hello, everybody. Hello, Raiders. Welcome. So I'm assuming that everybody was also here yesterday. We are actually making progress on the Radix tree now. I actually just started right now. So I'm done with my abstractions, and now I created my first node definition, and I'm reading the C source code of anti-res Rax, which is the Radix 3 implementation in Redis. And yeah, so we're going on an adventure. So I'm actually literally looking for where to start, and which is probably going to be the Rax init function, some kind of. There we go. Rax new. That's what we want. Rax new. Allocate a new Rax and return its pointer. Out of memory. On out of memory, the function returns null. So what's in a Rax? Also, apparently a Rax, which is a type. Why is an instance of Rax using the same name as the type? Oh no. But what is a Rax? It's just a short name for a Radix 3. So this specific Radix 3 implementation calls itself Rax, which is, Radix 3, but shortened. Okay, so what does a Rax have? Num elements, num nodes, and head. Now, you know what? This reminds me. We probably can see the Rax definition in the header file. This is a C project after all. So Rax node we know about. But is a Radix tree? Sorry, this is not going to be probably an answer that will help you much. But the short answer is a Radix tree is a compressed tree, as in TRIE. Tree, try. I don't know how you guys call it. And so then if your next question is, what is a tree? It's data structure that you can use to hold the strings. To be, you know what? I would suggest to Google what's a Radix tree. I'm gonna get into it more as I make progress, but the high level picture of what a Radix tree is supposed to be, I think probably Wikipedia does a good job at give you, an overview. There we go. So a Rax has a head, makes sense. That's what I call the root. It has a number of elements and a number of nodes. So let's do that ourselves. So we have root. We call it head instead. I think I prefer root. Okay, there we go. We have the same thingies. Okay, back to this code. So when we create one, it has number of elements 0, number of nodes 1. Head is a new Rax node created with 0, 0. So we'll have to see what Rax new node is and what these numbers mean. And then this is error handling in case that the allocation fails. So let's go implement this on our end. So pub function init. In our case, we don't do new, we do init in Zig, and we don't heap allocate forcefully. We just don't do that. If you want to put the Radix tree itself on the heap, you can do that. And I'm actually curious why anti-res doesn't just return abstract instance, but I don't know. C things for C developers. So what is this file? We need to do this const Rax is this. So this is a Rax. We return a Rax. It works like this. Init takes in a GPA. And then we basically try to create a node, which, by the way, we do here with an error. So we do try gpa.create. Actually, no, we can't do GPA create. What am I talking about? We need to use flex. We need to do flex.create. And the type is going to be node. GPA is going to be our GPA. And lengths, and this is the thing. Oh, that's what those numbers are. Lengths is the number of things. So this is going to be... this is going to be interesting. So this is going to be bytes length 0, pointers length 0. We try. This is going to be a node. Then we return a start that has root is node. Elements is 0. Nodes is 1. Okay, so this is a Rax. We're creating a Rax. Let's see. Are you trying to implement a Radix tree in Zig? Yes. I'm assuming this means that it hasn't been done before. No, it has. This is actually not even my first time doing this. In which I ask, is Radix tree a new data structure, or is it just not commonly used? I think code with Josh, I think I can expand your mental model around this stuff a little bit in a way that you will find useful, I promise. The idea is this. When you talk about a data structure in computer science, you are always talking about a family of data structures. When you say a tree, you're talking about something shaped like a tree. But how that is implemented in concrete terms can vary dramatically. You can take a tree and make it actual individual locations and then use pointers. You can take a tree and actually stuff nodes in an array list and use indices in the array list to point at another thing. You can have trees where the parent has a pointer to the child and the child has a pointer to the parent, or one way only, or both ways but by XORing pointers. You can you have a huge variety of options whenever you're implementing any single data structure, because a tree is a family of data structures. A Radix tree is a family of data structures, if you look at it that way. So you can implement it in many other ways. I made an implementation already, but it wasn't great. Now I'm aiming for implementing from doing a faithful port of a C library where I use the same techniques in terms of memory storage, except the only thing that I'm doing different from C is that I have new abstractions that I just implemented that I want to try out to see how they lend themselves to expressing this type of stuff. So long story short, not only you can implement things differently because maybe, you know, it's the same concrete things at the end of the day, but then you're using a different, you're giving different names to things, roughly speaking, like you organize things in a slightly different manner. But there's also like huge different ways in which you can organize memory and like do specific operations. So all of these are meaningful. Long story short, there are probably other Radix 3 implementations in the Zig ecosystem, but they are going to be different than mine. Potentially, I don't know. Maybe somebody also already did this work, like they implemented this specific C library, but in Zig. So somebody else might have done this. But in any case, even if they did, they are not going to use my same technique. They don't have this because I made this just now. Or you know what? Most probably, I actually, you know, don't have global visibility. But but I think the core point of what is interesting is that there is no one tree, there is no one Radix tree, there is no one hash map. There are like, all of these are families of data structures. And the same is true also for parsers. Whenever you're thinking, oh, I want a parser for this language, there's always a parser. There is no one true parser for a language. You can have multiple that excel at different things. There are internally structured in significantly different ways, and you will need all of them potentially depending on what you're doing. For example, I made a JSON replacement language, and I have, I think, 3 parsers in it. One is for the LSP, designed to work well with incomplete data. One is type-driven, where basically it's a parser that doesn't create an AST memory, but instead immediately deserializes strings into your target type. And then there's one that produces an AST, which is also used by other tooling. So this is what I have right now, but you could probably make many more other parsers that excel at different things. So keep that in mind. Everything is always a family of things. Hello, Karitam. Jess in Berries. Icon, hello. Are you doing Patricia 3 later? I don't think so. I think I want to work on this use case more. Isn't a Patricia 3 a Radix 3 with some more assumptions about your data? Could be. I don't know. I don't remember. I heard about Patricia. I think I heard about Patricia in the context of Julia a long time ago, like the Julia programming language. I don't remember the details though. But I don't know. For now, for now, my goal is this. I want to re-implement this C library because I want to test if this abstraction actually does improve the code rather than doing the pointer math manually. Okay, so we have init. Then what do we need next? Rax new. Rax realloc for data. Let's see. Realloc the node to make room for auxiliary data in order to store an item in that node. On out of memory, null is returned. So this is another interesting thing. So So here, Anti-res is saying a node can contain a value or it might not. And by the way, that reminds me, you know what? I'm doing this wrong because racks cannot be like this. And even the node cannot be like this. I think that, oh man, I think we need to do this. Pub function racks. And then you need to give me a type. Why? Because this is a key value store basically. So you need to tell me what's the child type. And then in here we do return struct blah blah blah. Now this is not node. Wait, where did I put node? Oh, I deleted node. Did I lose it? No, I did not. Okay. So this is not node actually. This is racks. Let's call it R maybe. The problem is that I cannot call it racks because this is going to be a racks already. So maybe we can keep using this instead of giving it a name because we don't do it often. Yeah, let's use this for now. Then I don't know. Maybe we'll find a solution in the future. So this. Okay, and then we're gonna have this guy. This is a node, and this node points to node. But here's the problem now. Here lies the problem. The problem is a node can contain a value or not. And the idea is this, that basically isKey tells you if this node needs to have also a value or not. And so there is this problem where we want to put somewhere something that might or might not be there. Oh, here's how it works. Holy shit. Holy shit. Here's how it works. Of course. That's how it works. Instead of having isKey or isNull, actually no, we do keep isNull, but then isKey is not really a boolean like this. It needs to be like this. It's value, and then value is a flexible array of type T. Parent is this. Name is value. And length type is a U1. It either is there or it's not. So we keep around the U1. This is what isKey was, but we use it also to drive the concept of whether we want this thing to be present or not. Jesus, this is insane. This is insane. The problem is that we can't put this after this. And this might be bad. So here's how the original code looks like from Anti-res. And this is something that we can take a maybe creative liberty with. So in case of anti-res, so what I just said, like the value is this guy in his case. But in his case, this guy is at the very end. It's after this, it's after this. It's not immediately after. So, and in our case, we're moving this up here. Is this good? Is this bad? I don't know. Je ne sais pas. Should it actually be after bytes? I'm actually not even sure. Maybe it should be before. Because I guess the assumption should be that this guy has a bigger alignment than these bytes. So it should probably be before, I'm guessing. I think that's how it should be. Is null. What's the layout? The value, the bytes, and the pointers. I think this is fine as is. Okay, so now we need a value. Also, value should be 0. No value in the beginning. Okay, let's put our test to good use. So const, I'm gonna make a rax of, I don't know, u24. Just a super annoying value type. Actually, what am I doing? Const r of type rax u24 equals dot init. Const GPA equals sd testing dot allocator. So init is gonna be GPA. The try is gonna mess this up, isn't it? Unused local constant. Well, yeah. Well, let's just see this work, and then let's do it like this. Expect r.nodes equals 1. I don't know. Does the try make this work? Expect the type void found com time int. Instead of flex, we have a programming error instead of flex. Pointers will definitely have a bigger alignment than U8s. Yes, but I can't. But it has to be the last one because this is the one that we don't keep count of, and we cannot do the inverse. We cannot keep only the count of these and not of these. Although, actually, let me think about it. No, we really can't. You know what? That said, though, I think it's a good question. Why did anti-res put pointers at the tail? Okay. Well, you know what? Let's just get a basic version working, and then we can think about these details more later on. Okay, what is the problem now? Expected type void, and instead found com time int. Right. So in flex, I think we might be missing out something in create. Because in create, for each field, we do the sizing, and then we do this. But wait, we're doing this. If field.type.child is different than void, then we do this. Otherwise, we don't. What's the problem, dude? Why are we doing this? Expected type void found com time int in 119. So this test is failing. It's not working as intended. Field type child is different than void. Okay, for debugging purposes, let's print these names. Please don't make this a let's see, prints value bytes pointers and then panic. So it's pointers, yes, which has and they all have a child. So what is the child? U24, U8 node. Oh, is this me being dumb? This is entirely me being dumb. We don't care about child. We want to know what is the len type of that field. So we can put it here in a decal, to be honest. But we have this information also here, so no point in duplicating it. So it's more metaprogramming, but it should be fine. So yeah, that's entirely on me. So this is not child. This is type of field type. But then we can access len. So I guess it's is there like an std meta field type function, please? Would be nice, huh? I guess we have fields, field info. I think field info is what we want. There we go. Okay, maybe messed something else up, but this is roughly the logic. Expected meta field enum blah blah found string. Okay, so it doesn't want a string, it wants a dot. Okay, so it works, and now we leak, which is actually delightful. Let's not leak then. Let's add the init, I guess. So how does it work? I guess we could call the init recursive. We can do something like this, like r.root dot the init, or like we just call the init on that node, and then we do dot recursive, something like this. And then the node will try to the init itself, but first calls all the other ones. So node needs to have pub function the init. Node. Then mode. This might not be the greatest way of doing it because this relies on recursion, which freaking sucks. But then we can do this. Switch. Actually, switch nothing. This is something like for n dot pointers dot slice. Oh, but we do need to do stuff, huh? It's like this: const ptrs equals on n dot ptrs dot slice, and then if almost okay, const ptrs is switch node dot layout and then dot compressed, or what is it? Merge split. Okay. So if it's merge, it's n dot pointers dot slice. Otherwise, if it's split, and actually this is slice. Let me think about it for a moment. 0 dot dot 1, and otherwise it's n dot ptrs dot slice to 0 dot dot n dot bytes dot len. That's how you compute it. And then for each one, p dot the init, pass down GPA, and pass down dot recursive. And this actually is only if it's if mode equals dot recursive, then we do this. And then once we're done, we can free ourselves. Shit, we need to keep around this. Oh, this is interesting. So never mind, we want that value separate. Okay, so const ptrs len. Let's do it like this. Yeah, ptrs len is this without the slicing. There we go. There we go. This works. Holy shit, this is okay. I'm loving this. This is pretty decent. The math on all this stuff otherwise, it's annoying to express. Although you can always encapsulate it, I guess. That's which is kind of what we're doing. But this looks cool. So switch layout. This is the slice. This we make recursive. And then we call flex.destroy on this thing. Okay, let's see if this works. Expected type, pointer, root flexible array, root racks, blah, 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 found a line for const root flexible array. What? Expected type, expected a pointer to flexible array, but instead found a pointer with a weird alignment. Oh, wait a second. Does this have anything to do with our thing? It's a pact struct though. What is the problem? And no, technically we haven't changed anything. Where do you see this problem? It's a boolean u1, then another u1, then another u1, and then a u29. So pointers is the one that complains about. So okay, we're expecting this, and I think the problem is entirely that there's a weird alignment. Why is there a weird alignment? Cast discards const qualifier. Oh, I guess this is the biggest problem. That we want immutable slice, and we're not providing immutable slice. Why? Because our node is const. But does that matter? That shouldn't matter, though. Does this need to be a mutable pointer? To be fair, no, it does not. Let's see what we're doing here. Tag name. Then we do field fire pointer on this. Align cast. So we can take this as const, I guess. What happens then? I think some other metaprogramming will fail at that point. Yeah, because we need a const cast. Okay, let me see again what we're doing here. The problem is that this is a const. If I turn this into var, will this make it better? No, it doesn't make it better. It does not make it better, which is surprising. Oh no, maybe it shouldn't, because I'm saying that this node here is const, and slice requires me to do this. So let's do this. Now, are we fine with this? Because in the init, well, maybe we should just accept a mutable pointer to node, and then we're good. Yeah. Type u1 cannot represent integer value 4. Guess we need some kind of int cast. I don't get it though. This is weird. Oh no, it's 78 that has this problem. Okay, that makes sense. 78. Offset is defined the use size. And this is value.len times size of. What is going on? Why are we thinking that this is a U1? I mean, I know what is a U1 in here. This guy is a U1 in one of our cases. So, oh, that's weird. I guess we need to widen it first. Expected type use size found void. $156. Oh, same mistake. Same exact mistake. Okay, problem is expected type use size found void. Are you sure about this? Oh, we flipped around the conditions. Okay. Expected type use size found void. Again, 78. You know what? This might come in handy again. 78. Um, these should not be possible. Expected type use size found void. This should not be possible. This should not be possible. I mean, we can do this, but this should not happen. Expected type use size found void. Okay, there we go. We got a failure. What's happening? Incorrect alignment. Out of curiosity, let's try for a moment a less gnarly test case. Let's try use size. Should be easier to make happy. And we still fail. Okay, so we still get incorrect alignment, so there's something big wrong. And wait, what? This? Incorrect alignment of this? Hmm. Oh, come on. I want the pointer, man. How do I get a pointer for matter P? Oh, no, I'm dumb. It's star, of course. Uh, oh, no. Oh, no. um, no, wait, actually, this is correct. Wait. I'm looking at the wrong thing. This is not R that we want to look into. It's root, which is R dot root. It's the root node that we want to look at. It's the one that we also disagree on things. Yeah, and this is bad. This is bad. Why do we think this? So when we're calling slice in racks, we're getting bad stuff because we are thinking that we're going back to the parent, but somehow we are not. So it means that I'm borking the math before. And no, but you know what? It's not even the math before. Like, wait a second. What am I even supposed to do, man? It's what? So notice how we're always fucking up ever so slightly. So root thinks that the root node is at this address. And here we are doing math wrong, but also at the same time, it's not us doing math. It's not us. Unless we're copying something, but we're not, are we? So who's calling slice? It's what's our call stack? The init. So the init starts with the 3. You know what? Maybe we should call it 3. That's yeah. Okay, so from this guy, we call the init that gives us a pointer to the node. I guess the question is, do we agree still here about what this is? Or do we already disagree there? No, so far we agree. And then we then end dot pointers dot slice. And you know what? I bet you that this is field parent pointer fucking up with packed, I think. Yeah, look, without packed, we agree. Oh no. Field parent pointer is barking on a packed struct. And then we segfault. That's also not great. That is also not great. That is unfortunate. Wait, can I reproduce in a simpler setting? What's our specific case? We have a Boolean. Although this is not exactly the same. This is a this is more like what we have. What am I doing? What is happening? Okay, this is all fine. You can't debug comp time stuff. Well, you can debug what the compiler does, no? I mean, unless you make a debug build of the compiler and then you start stepping into the compiler as it's building. But Right now, I'm just trying to replicate the behavior, and so that I can make a repro and see if it's me thinking wrong. You know what? Maybe I'm wrong in thinking that this should be size 0. I don't know. But I think it's more likely that it's just field parent pointer that it's doing wrong math. Wait a second. Did I fuck up the names? No. Value, bytes, pointers. Okay, because this type of error, it also sounds also a little bit like I'm messing up one of these things. Like I'm trying to use a wrong pointer for the wrong name. So here's the name is that we're using is pointers. Yeah. We are disagreeing. Um is this because of this undefined? No. Okay, so we are definitely seeing a tiny difference in how this stuff is calculated. Something that should be size 0 is not assumed size 0, or there's some, I don't know, some alignment stuff that is thought of, but that doesn't make sense. Would this help? This does not help at all. Well, I think we found a bug. Let's see if anybody has reported this stuff. Yep, there we go. When was this opened? A month ago. Yeah, somebody else experienced this. What? Based on what? Oh. Oh, 1 year ago. Holy shit. You're right. Jesus, I didn't look at the year. Well, I'll say this in my defense. No, there's nothing to say in my defense. I just didn't look at the year. Sorry. Wow, I did not expect this. So I guess that for now we continue without pact. That's kind of what we have to do, right? By the way, you take this out. Pointer increases pointer alignment. Yeah. Yeah. Okay. Well, this is bad. Okay, so this means one thing though. Let me see if I can send this to Mlog. Compiler bug fixing stream. I don't know if this stuff is really something that I can try to take a look, but I think there are good chances that this might be a very quick fix for MLAG, who does front end work, and I don't know. I've never touched this stuff. So I don't know. We could attempt, but here's the thing: if we take out pact, we can make progress. So the idea is this: we take away pact from node, and so our tests fails now for a different reason. You can see that without pact, it works. Also, what was the issue that pointed this out? This one. Oh my god, come on, man. Why is clicking somewhere in the page making me move the web browser? Like, since when? If I click down here, it doesn't happen. But if I click up here, it works. Like, I get it. It's close to the top. But why? Software, man. Okay, so let's see. So we have a crash, and this is on us, basically. So what is happening right now? Oh, you know what? This might be on me. Here's what's happening. I think this is a bug on me. Here's what's happening. When we create a node, and look, we never initialize the freaking node. Right now, this node is it has some fields set, but not all of them. It's missing these guys. We haven't is null, and we haven't set is null, and we haven't set layout. So we should do that. So is null and layout. Merge or split. If it's, I think this should be split by default. Because if we make it merge, then we will assume that there is one of these guys unconditionally. And that's actually bad. Unless we actually say that we do put one of these guys here. Okay, so let's do that. Let's say that for now this is merge, the layout. Okay, so with this, we should not try to allocate stuff at random. It seems that we still do. So we still switch, and then segmentation fault. While trying to access n.layout, node.deinit. Oh, look at this. Uh-oh. Yep. That at 0 means something, doesn't it? So it means that in here we're not... Sorry, I got it wrong. I said merge, but no, it's split, the right starting point. There we go. Now it works. Well, it prints stuff that we can take out. And now we succeed. Okay. So we did a good job here. I'm kind of thinking whether we should, like, I don't know, give a better API for this, but I guess it's fine. Maybe create should not attempt to set these values at all, and you're expected to set them afterwards. So that you can use this syntax, you can do node dot star equals this. And then you can also do like there's some redundancy here, I guess. That's kind of my point. Hmm. Okay. So next. Realloc for data, set data, get data. We'll see how this stuff works. Rax add child. There we go. Let's see. Let's see. Add a new child to the node n representing the character C and return its new pointer, as well as the child pointer by reference. Jesus. And then there's also parent link. Whoa. Additionally, pointer parent link is populated with the Rax node pointer to pointer of where the new child was stored, which is useful for the caller to replace the child pointer. If it gets reallocated, on success, the new parent node pointer is returned. This is a that stuff. Maybe it should be create merge, init merge. No, this part is not important in my opinion because these are internal APIs. So this is not something that a user is going to use. So sure, I need to get it right, but you will find that this code is going to be littered with just getting the algorithm right. Look at the C code. The C code is doing stuff. There's triple pointers, and it's just the nature of this type of data structure. Sure, you can make it a little bit safer, but we'll see. That said, you know what? I don't exclude that maybe in the future this will make more sense. But for now, just because of those fields not being initialized as like forgetting to initialize those fields because I called create, that to me is not enough. Compress node. Turn the node n that must be a node without any children into a compressed node representing a set of nodes. Link one after the other, blah, blah, blah. The node can be a key or not. Right. Track slow walk. I think that what we want next is the insert function. I think we should start from the insert function. And then as we implement the insert function, we will need to implement some of these guys as needed. So there's Rax new node. For example, here, Rax new node gives you the number of children and the number of int data field. This is like the data field value. Like if something should go there. Let's see. If data field, then node size plus size of void pointer. Okay, so that makes sense. But this is a Rax node API, so we don't care about those. Those are internal APIs. We care about Rax APIs. Where is it? Rax low walk. Oh, there we go. Rax generic insert. Insert the element S of size len setting as auxiliary data the pointer data. If the element is already present, the associated data is updated only if override is set to 1 and 0 is returned. Otherwise, the element is inserted and 1 is returned. On out of memory, the function returns 0 as well, but sets erno to eno mem. Otherwise, erno will be set to 0. Okay, I think that's what we want. Also, what is a non-generic insert? Because we have this generic insert This is where the like core of this stuff happens. But Rax insert, okay, Rax insert calls Rax generic insert. Let's see, overwriting insert, okay. Just a wrapper of a generic insert that will update the element if there is already one for the same key, and then there's try insert, non-overwriting insert function. This is if an element with the same key exists, the value is not updated and the function returns 0. And then Rax find. Okay. So we kinda want this, basically. Rax insert and Rax try insert. So let's add them next. Pub function. And I like getting this whole algorithm right is gonna take a while, because this is like a big chunk of the logic. But once we have that, at least we have insertion, so that's good. So function is going to be, I guess, insert. So in Z we have append for lists. We have, what do we do for hash maps? Is it a hash map insert? I don't think it is. We have put. We have put no clobber, that kind of stuff. So this would be put. Input 3 allocator, and then the item. Well, we need the key. And then we have the value. Can error out, and otherwise returns what? I'll say that it returns void for now. Okay, so this is the bad boy that we need to implement. This is going to be intense. Hello, Andrew. How's it going? Well, I discovered that packstructs just do not work with field parent pointer. The math is borked and has been for a long time, which is surprising. We should not have this. Messing with packstructs should be something that should work. Okay, let's do the work. So, this bad boy function, huh? Lots of work happening in here. Let's see. We might as well also read some of the comments, because they also help understanding what's going on. Okay, this one has Rax, the data, the key, sorry, the data. There's this also, old. Oh, in case of an old item. I guess this is basically get or put, honestly. This is like, with all due respect, this is like a bad, a crappy get or put. So you know what? Since this is structured this way, let's just implement it in the form of get or put. So get or put, and it returns a, I don't know, I can call it gop. Although, wait a second, because the problem is that No, there's actually no problem. Yeah, it's get or put. It's a get or put, but we cannot return the key pointer because there's no key pointer. We can just return the value pointer. Although, something like this, pointer to t. No, it's not exactly like this. It's const. It's a pointer to t. Which you can use to write the t. And so you don't pass in the value t. Okay, this is more Ziggy, I would say. Is this the real Andrew? You know, there's more Andrew. There's more than one Andrew on the planet, and as much as you know, Zig's Andrew is, okay, a cool Andrew. You know, I think also the other Andrews deserve to be considered real Andrews. Okay, let's see. Size ti. We have I and j. J is the split position. If rack slow walk, which okay, so we'll have to implement rack slow walk, stops in a compressed node, so that would be for us a merge node. The index j represents the character we stopped within the compressed node, that is the position where to split the node for insertion. Yes. And so we keep around also h and parent link. Okay. Yeah, let's prepare some of this stuff. Why do I have cut? Man, the web, huh? We don't know what I is. Okay, I think that I tells us. Okay, I think I get it. So I is an index inside key. Index inside key. Then j is index inside merge node up to which we matched key. Okay. H and parent link not immediately clear, but I think the problem is that the fact is that this node always points down; it never points up. And so as we walk down, we also keep around this function. We also always keep in mind it will keep around a pointer to the parent node that it looked at previously, and it will return it here. so that if we do, basically we move around then the current node that we're at, because we're manipulating it to make space for the new string, that might cause us to realloc that node, or like think of it as like freeing it and recreating it somewhere else. And so in that case, we will want to set the pointer, set the relative child pointer in the parent. And that's what parent link does. Well, that's a double pointer. Why is it a double pointer? Why is it parent link a double pointer? Because it's an out parameter. Because this function uses parent link as an out parameter. Do we really care about out parameters that way? Do we care about out parameters that way? Also, wait, is it really double pointer and then we do ampersand here as well? What? It is a double pointer and we take a pointer from it, right? Because, well, no, wait. I would understand this being a pointer to a node, and then we pass down a pointer to this guy, so that you can write in this guy a pointer to a node, but it's a double pointer. So I guess we are not pointing to the parent. We are pointing to the slot in the parent where a pointer to the child resides. And we grab a pointer to that. And that's what we write here. Man, freaking triple pointers, huh? So I get it, but do we really need a triple pointer here? Really, the triple pointering is just because we want to use this as an out parameter, and it honestly freaking sucks. I'm thinking that Rax low walk should not do that. And it should always return the parent link instead of just returning I. That said, I guess it is nice to be able to write immediately here. You know what? I'll keep it like this. I'm not entirely against it. I don't love it, but I'm not entirely against it. So this can be like this. R dot slan becomes key for us. H, we don't know yet what it's gonna be. I guess H is like the result. It's the matching. It's the node where we basically end. More precisely, this is a pointer to the section of the parent of H. Well, this is this. This is basically parent of H dot PTRs at this is this. Yeah. I don't know what the last argument is. Let's see. Function rax low walk. Then 3, although this can be const because we don't change anything. Then we have h. Then parent peeling. It's a people pointer to node. And then I don't know what the last one is. Well, let's go figure it out. Ah! GitHub. Okay. Low-level function that walks the tree looking for the string s of len bytes. The function returns the number of characters of the key that was possible to process. That's I. If the return integer is the same as len, then it means that the node corresponding to the string was found. However, it may be a key in the case that node's key is 0. Sorry, may not be a key in the case that a key is 0, or if simply we stopped in the middle of a compressed node, so that split pose is not 0. Split pose is J. Where's split pose? Is that the input? Man, the arguments are a disaster. Okay, so this is Rax. This is the key that we're matching. Stop node, not a bad idea. Not a bad name. Stop node p-link. Oh, I also ended up calling it p-link. And then so J is called split pause. That's fine. Okay, so p-link split idx. It's a pointer to usize. Then what else? Actually, these are not usize. These are actually U29s if you think about it, because a node can't really be bigger than a U29. So let's make this a U29. And same with this one. And same with this one. Okay, so we have the split IDX and Rax stack. Right, the whole Rax stack idea, which we're passing null down. Is there any opaque for now? What are you doing, by the way? I'm re-implementing in Zig this C library called antires/rax, which you can find on GitHub. Okay. And so this is the algorithm, which is not too bad. If you look at it, it's really not too bad, honestly. Which makes sense because I think that like navigating a Radix tree shouldn't be too insane. With the only difference that we don't have a Rax stack, so the stack of parent nodes is an optional feature that we might do or not do, and so I guess fine. Okay, let's copy this code because I'm gonna implement it very closely. Okay. So var h equals r dot root, then var parent link is ampersand, yeah, r dot root slot in pointers. Yeah, it's not always pointers. It's usually pointers, but it's not pointers in the case of the root node, which makes sense. Good design. Good design. Okay. We have I and J. No, you know what? Actually, I'm kind of dumb because a single node can only have up to 29 bytes, but the string itself is usize. What am I doing? Sorry, this is this. This is this. Yeah. Okay. Position in the string. You know what? Let's do it like he does. Position in the string. J. Position in the node children. This one is a U29. Okay, so this is the main algorithm. So while h size and I lower than len, so while h dot bytes dot len is greater than 0 and I is lower than what? We're missing one argument here. We're missing the key. So Sunday backtracking doesn't seem a bad idea, huh? Although I don't know how we access this in testing. Although we should. Oh no, I remember. It's the problem is std.log integration. That fucking sucks. Well, we can add debug printing after the fact. It's fine. So unsigned char v is h pointer to data. If it is compressed, so if it's a merge layout, okay, let's ignore for now this outer thing, but let's look at this switch. Switch h dot layout. So merge is the compressed layout, and then split is the other layout. If it is merge, then what we're doing is we're moving forward both our string and our index into those bytes. We're moving both of them forward at once. If we find a mismatch, we break. And if j is different than h size, we break. I type a switch. Yeah, I did. There you go. Okay, so let's implement these both going forward thing. There's also an interesting condition here because this is a double condition. So we're saying we need to make sure that we don't try to overflow. We cannot overflow the one or the other, basically. Kind of. That's the point. So here's how we can do it. I think in Zig we can do a for loop. I think we can do it like this. Minimum length is min of key.len and h.bytes, also const bytes equals h.bytes.slice. .len, although this could very well be just bytes.len. Okay. And then we do for bytes, comma, min len. Like k is going to be for the key, and then node is going to be for the node, I guess. We can do k byte and byte. And we say if k byte is different than n byte, we break. But here we're also doing math on j. Here we're not doing math on j. So every time we enter, I guess we want to do I plus equals 1 and j plus equals 1, which is what we were doing also here. Yeah. K byte and byte, keep increasing. If actually, wait a second, do we increase before or after? It doesn't matter in which order we do this. Well, no, wait. It does matter in the case of uh, a mismatch. So we increase after after the check. First we check because let's say that the first character doesn't match, then we want to leave I and J to set to 0. Okay. Hello, Kanka Zero. Welcome. Okay, so we're implementing this, and then we say after the for loop, we say if J is different, then what? Each size is the length of the node, so that's bytes.len, and we break. Okay, so this is this part done. Then there's the other one. So it's the split case. The split case works like this. We don't move forward I because we are looking to match any of the characters in the node. So we don't move forward I anymore. We just move forward J. And so as long as J is a valid index into the node array, we can keep looping forward. Here, if there is no match, we break. Here, if there is a match, we break. And if j equals size, we break. And then there's an I++, because, right, if we did not break, let me think about it for a moment. This break is fine. This one is not fine. Let me see what this is. J equals h size. This means that the character that matched was none. Okay, so there was no match. Okay, so this is the case where there was no match. Okay. Okay, perfect. Break if we didn't match everything. Okay, so down here, the logic is different. So I guess we still want to do this. And here we do for, I guess, 4 bytes. I guess. Do we want an index? We actually do not want an index here necessarily. We just want to increment. We just want to do J++, so we don't care. Okay, 4 bytes. We say if key at I equals n byte, we break. If, oh, and we need to increment J also. If J equals bytes.len, then we break. Okay, a character didn't match. You know what? Now that I think about it, I think that this is kind of bad. This works like this. Look at this. This is like this. Can Zig break the outer loop? Of course. Yes. Yeah, so basically, if we don't break because of a match, then we enter the else branch of the for loop, and then we're gonna break the outer loop as well. And if we don't break, then we increase this. Can we do something similar here? Let's see. There's a for loop. We break on a mismatch. And basically what we're gonna do is if we exit the for loop, we're gonna break, then we want to break as well. I think this should be like, this should stay like this. Because using the else case doesn't really help us. Yeah, the else case does not help us. Although, no, you know what? Wait. No. There is actually something to help us because look at this. Oh no, this is this is actually irrelevant. This is a sad C moment. So look at what's happening. Here we're saying if we find a mismatch, we break, and then we break again on another condition here. But what is this condition? This condition is that we haven't reached the end of the loop. So this is the condition of if we broke early from the for loop, then we break again. So this is basically us trying to break to the while loop and not being able to. Well, check this out. There we go. No more C-isms. Nice. So I think we can take this out then because we have implemented it all. So now there's this part afterwards in the while loop still. So here, let's see what we're doing. Oh, TS is the stack pointer. I think I'm not going to implement this now. I'm going to put a delicious panic to do instead of implementing the functionality. So then, okay, what are we doing here? We're saying Rax node first child pointer. So here we're grabbing a pointer. Why is this a pointer to... Oh, right. Okay. God damn it. See. Okay, so this is this const children. Children is node dot ptrs dot slice. And then what we do is, if it's compressed, we set j to 0. Let's see. A compressed node, only child is at index 0. Yes. Otherwise, I guess we leave j where it is, and then we do mem copy. What are we mem copying? Also, I was saying n, but here we have h. H is the current node, apparently. So, okay, so this is h. But why are we doing this? What are we mem copying? Oh. Wait, why is this a mem copy? Why is this a mem copy? What? So this is like this. Const child index is switch h dot layout. And if it's merge, then it's... well, you know what? I guess we can do it with an if. I think that's fine. So if h dot layout is dot merge, then we do j equals 0. That's fine. And then instead of children, it's child. And child is going to be this at j. And we assign this to h. There you go. This is not that hard. Okay, and then parent link. And then parent link is this. Parent link is ampersand h.ptrs. Well, I guess we can do it like this. This is the parent link, and then j is parent link dot star. There you go. And then j is set to 0. If the new node is compressed and we do not iterate again, set the split position to 0. To signal, this node represents the search key. Okay. I'm not sure I'm following what this is meant to be, but it's fine. So with this, we are done with the while loop. Now we're left with what should go outside of it. So if stop node dot star is h. Wait a second. Where the heck is stop node? H out? Yeah, stop node. Okay. Wait, you can avoid passing it? Really? When do you not pass it? Well, okay. I don't know. If peeling, I guess you don't have to pass these things. I guess if you don't care about them, you don't have to pass them. That makes sense, I guess. If split pause, this is stop node peeling. What is split pause? Oh, it's split IDX for us. That also is optional, I guess. Okay, there we go. Invalid left-hand side assignment. Okay, happy now? Unused capture. Yeah. Okay, so this should be it then. Almost. No, this is it. Okay. What's the problem officer? Let's see. Unused function parameter. We haven't used GPA so far. Yeah, I know. No, don't worry. We'll get to this. Okay. So we have implemented rack slow walk in theory. Let's return to generic insert. So we have done this. Then we need to do this other stuff. Please, GitHub, stop. If I equals len, we walk following the whole string. If you're not in the middle of a compressed node, the string is either already inserted or this middle node is currently not a key, but can represent our key. We have just to reallocate the node and make space for the data pointer, indeed. Which in our case is not a data pointer, it's just a data value, whatever it needs to be. So this is one case. This is like the easy case. And then we have the complex cases where we need to take a node. We're like in the middle of a node. We need to split it or we need to add stuff. Like we need to deal with a bunch of cases. And there's a bunch of sub cases for each one of these guys. So yeah, there's work to do. Oof. Okay, but we can do this. Okay, so after Rax low walk, we do if I is the same as key.len and not h is compressed, or so if h.layout is split or j is 0, this is saying not in the middle if j is 0. Right, this is, I guess this connects back to us setting j to 0 earlier. Okay, insert node representing a key exists, so we need to make space for the pointer if needed. Again, they keep saying pointer because in C, since there's no generics, they just pass around pointers, void pointers. In data structures, in our case, we can do better, so we do that. So is key is null override realloc for data mem copy. Man. Yeah, we need to do the mem copy, huh? Also, realloc for data. Why is it always realloc? Why is it never resize? Oh, I guess because it kind of has to force realloc because a resize. Well, resize for data shouldn't be a problem. Like you should be able to resize for data, should you? At least in his case, it should be possible. In our case, it might be problematic. Actually, in our case, it's definitely problematic resizing for data. Oh shit. No, I guess we can still do it. It just needs to be done smartly. Okay. Or no, mem. Oh no. So this is a. Let's see. If it's not key, I think we might need to have take some minor artistical freedom in re-implementing this, because we're doing the get or put pattern where we're saying um, if it's present. Yeah, okay, so this is how it is. Const get or put. Now I remembered. So that's how it is. This is the get or put return value. There we go. Okay, so this is gonna implement next. So give me a sec. I'll take a very quick bathroom break. Maybe I'm gonna make myself some tea. Actually no. Just quick bathroom break. I'll be right back. I'm back. And sorry, I lied. I also got something to drink. Which industry will see the biggest Zig adoption? I don't know. I can see Zig being adopted in hardware. I can see Zig being adopted in other kinds of, like, let's say, critical software infrastructure, databases, OSs, I guess. But your question is more specific than that. It's like, what is the industry that will see the biggest adoption? I don't know. It's hard to say. I think embedded stuff, but I really cannot say for sure. Okay, let's continue with this work. So let's see. If if it's not a key or is null and override, then reload for data. Oh, I just realized, like, this null optimization is if you're putting null, then we don't store a null pointer, and instead we use the is null bit. I think we can keep is null. Yeah, I think we can keep is null. Hey, Matt. Hello. Hello, hello. So this null optimization is pretty good. We should keep it. The only sad part about it is that oh no, there's nothing sad about it. Oh my god, check this out. So we can do it like this. Holy shit. This is actually cool. We can say value is based on reflection. So if type switch type at type info of t, and we say if it's optional, then we return opt.child. I'm assuming it has child. But we need also, I think, to do something else, maybe. No, you know what? It's fine. So child else. If it's not optional, then we keep then value is gonna be t. Okay. And then in and let's do it like this. Yeah, and then is null. Holy shit! Check this out. We say if um if type info of t is optional, then it's a bool. Else it's a void. Oh, it's not. Oh, you're right. It's not uppercase anymore. Yeah, I'm a Zig boomer, I guess. um, you know what? I'll say this. I haven't done metaprogramming in a while. Like I've grown out of my metaprogramming phase. You know when you just started using Zig for not a long time, and let's say like you're like a Zig teenager, and you just can't stop playing with metaprogramming. Like you're touching your comp time all the time, right? I grew out of that phase basically. So it's been a while since I since since I've done this stuff. But we can get clever here. So we can say, look, this is null optimization, which is good to have. We only do this field is if the type that we're given is optional. And if it's not optional, we don't even bother. And that actually gives us the ability to do something else. Like we can put that that beat somewhere else. Where do we put that beat? Maybe we can change this and parameterize this a little bit more. From U29, we can turn it into a U30. We're not just adding a bit to layout. What do you mean? You're not just adding a bit to layout. I can do that. I guess my question is there a better way of using this? This is a node in a Radix tree. So far this header is 32-bit. It's not packed because of the packed struct field parent pointer bug. So this is currently not packed, like temporarily not packed. So what I was noting is that the original C implementation, which is the one that I'm implementing, yeah, I want this to be packed, but it's not because otherwise nothing works. So yeah, basically the C implementation has this is null field, but um, but yeah, sorry. But the point is that because they use pointers, like for the C data structure, the only value type that you can give to the Radix tree is a pointer. It's a void pointer. So since we are generic, then we still can benefit from this because the idea is that the memory for the value. This is a struct with flexible array members. Well, with a flexible array member in C. And so the original implementation doesn't even allocate extra memory for the value pointer if there is no value in a given node, which makes sense because the majority of nodes will not have a value. But also it uses this bit to say, well, the value is null. So instead of allocating, 4 bytes or whatever, 8 bytes for a null pointer, we just flip this bit, which makes total sense. But in our case, T is not always going to be optional. If it is optional, it makes total sense for us to also avoid storing an actual value and just flip a bit. But if our T is not optional, then we can set this to void, and then what do we do with the rest? I don't know. What I'm guessing is that probably the smartest thing is to make this a U30. And I think maybe this should be parameterized. Something like this, null type. I don't know. Is null type. What am I doing? I guess. Let's see, unrelated, but I wanted to share that I've been writing some multi-threaded programs in Zig, and it's been super fun. Well, good that you like it. And you don't even have access to the new async stuff. Once it's gonna be out, it's gonna be cool. We have len type, and now I have other U29s that I think I'm gonna need to parameterize to len type. Len type. Here we go. Okay, and so this is not of type T, this is of type value. What's the recommended way to pick up Zig for someone that's approaching a low-level language for the first time? 3 suggestions. And they're like, they're in end. So you don't do one of those, you do all of them. Number 1, go to zigland.org, learn section. Here's the language reference. Here's the standard library documentation. Here's some information about the build system. Here's more stuff. Here's how to install Zig. Online learning resources. These are really important. Do check them out. Introduction to Zig, a project-based book. Zig.guide. Zig links, Zig on exorcism, and learning Zig. So, in particular, I would say, well, this is kind of a book made by the community, then by a community member. Zig.guide is basically use case based and helps you go understand what's where in the standard library. Like, oh, I want to access a file. How do I do this? Zig guide will tell you. Then Ziglinks is where you wanna start probably if you want the smoothest possible learning curve, which also means that if you're like if you're a quick learner, it might get boring actually. So be aware of that. But it's basically a collection of tiny broken programs with comments that tell you how to fix them, and then you basically do them one after the other, and you learn Zig syntax in the meantime and some concepts on along the way. People also like this one a lot, apparently. So do check this out. Okay, so this is suggestion number 1. Find learning materials. The learn section contains them. Suggestion number 2. Find a project that you have never been able to tackle before that you find interesting. Yeah, obviously you need to manage your expectations. You shouldn't try to tackle something too insanely complicated and hard because you're not going to be able to pull it off. But for example, have you ever written a parser for a language? Have you ever implemented a toy language? Have you ever implemented a ray tracer? 3D graphic stuff. Have you ever implemented an OS from scratch? Have you ever implemented audio processing? Like, have you ever done anything with audio? And the point is, when I say audio, for example, you don't want to aim for, oh, I'm gonna make a I don't know, Discord alternative. That's a lot of work. But for example, a simple echo program where you get access to your microphone, your headphones or whatever speakers, and then you are able to play audio back. That's already more work than it might seem at first glance. But for example, if you've only ever done JavaScript or Python, this kind of stuff, it's not really something that you can do easily. You can kind of pull it off, but it's janky as fuck, and you always have to depend on libraries and third-party things. But if you do it in Zig, you can actually do it start to finish, A to Z. Everything that has to happen to, for example, pipe audio from your microphone to your headphones, you are in control. You can have control over. For the other projects that I suggested, for example, an interpreter, there's craftinginterpreters.com for parsing and making a parser for a language. This tells you how to make an interpreter. This book doesn't tell you how to do it in Zig, so it's up to you to translate what the book suggests to Zig specific code, but it's doable. And the problem is that the point is that the book offers you a polished, curated experience that it has been packaged. Basically you know that you will reach a end goal, and along the way there's going to be well-defined sub goals that every time you reach them, then you will have achieved something, and you don't kind of get stuck somewhere and then you have nowhere to go. I haven't done crafting interpreters, but I've done operating system in 1,000 lines, and I've done ray tracing in one weekend. I've also done this one. If you're interested and you want to see how it went for me, you can go to ChristoIT/ChristoS. So this is the OS in 1,000 lines. What am I doing? Port send. And ChristoRTX is the ray tracer in a weekend. These repos also have links to the VODs, because I did this stuff always on stream, so you can see exactly the process. So this is the general idea, and it could be, for example, a CLI tool. So I gave you some, let's say, more daring ideas, but it can be even something simpler, like re-implementing a CLI tool from scratch and see how it goes. Maybe first you do that, and then you try to tackle something more complicated. This is suggestion number 2. So suggestion number 1, learning materials. Suggestion number 2, which projects to pick. Suggestion number 3, join a community. Join easy communities so you can get unblocked when you get stuck, and you can ask other people for help, and you can give other people help as you learn stuff, which is also good, because if you're willing to, that's how the help economy works. For you to receive help, somebody also will have to give help to people that know less than you, and might as well be you from time to time. What was I saying? It's not only that, but also joining a community allows you to see what other people code looks like, so you can learn more quickly what's idiomatic, what's a good idea, like clever patterns that maybe you're not familiar with. So grab learn materials, find a cool project, join a community. Lastly, this is, I guess, part of the third suggestion, so the community stuff. Go to zig.day. So join an online community for sure, but go to zig.day, and if there's a Zig day near where you live, there aren't a ton, to be fair, but if there's a Zig day near where you live, then consider joining it. There's a Zig day Portland. They're gonna meet August 2nd, so it's gonna be a couple days from now. And these Zig days are full day events where people do collaborative programming together. And the idea is that you use that to learn systems programming and how to make software you can love, which is a branded way of saying software that doesn't fucking suck. Is there a specific way to interact with protobuf in Zig? You mean like a protobuf library in Zig? Probably. Somebody probably made it. Zig protobuf. There's one Zig protobuf. There's another Zig protobuf. Oh, this has been archived. Wait, what? This was archived 10 days ago. What happened? The author recommends using. There we go. Never mind. So you want to use the other one. Okay. So here's one. So you can pick up this library and use it. If you want to know how to get started with the Zig build system, I also recommend this. There you go. Oh, you have one? I didn't even know you had one. It didn't even show up on Google. There's a Zig paragraph in Zig's tree. Yeah, Matt, GitHub doesn't think that your library is worth telling people about. Womp womp. Oh, there we go. There we go. Zig PB 2 years ago. Yeah. Okay. If this is not optional, disable this null bit. Well, let's do it like this. Okay. So what's the problem with get or put? Duplicate strap to name get or put. Oh. There we go. Okay, we can finally get back here. So, what we were saying is blah, 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 blah. If it's not key or is null and override. So the question is, what do we do if the current node is already key? Current node already holds a value. Although here what we were doing here is, what if it's not the case? If it does not hold a value? Kinda, because this would be the case where it does hold a value, but we also have override set, which is not what we're doing. So, oh shit. Now that I think about it, this is null optimization doesn't play well with get or put. Now that I think about it, freak. We can't do get or put, can we? Because of his null. Ooh, this is interesting. So here's the problem. If we do get or put assumes that when we return like a reply, that we have a value pointer, but the value pointer, how can I say, might not be there, but there might not be a value pointer if the value is null. So we can't do a get or put in the traditional Zig style. The original API accepted the value right away, which is kind of annoying because it means that it forces you to um, produce a value beforehand. But I guess we can give a method to get or put to basically fix this stuff. Kind of like this. Like we give it set, basically. And here we do this work. This will work. Set value, maybe. It's clearer this way. Okay, so here we say current node already holds a value. So if not node is key or, so this is not, so this is a condition that just increases memory unconditionally, which we do not want to do, but also node representing key exists. Yes, and that's fair. But wait a second. If this is null and override, then we realloc for data. Oh shit! So realloc for data is the one that makes it a no op if data is null. Okay, interesting. We're not checking this here. And then if current node we're operating on, why is it if h? Oh, because this can fail, right? The realloc can return null, so this is what this is doing. If h, we just run a mem copy. Oh, right, that makes sense. Wait, so if this fails, if this returns null, oh, there we go. There's the error handling. Okay, and then we say, okay, update the existing key if there is already one. Otherwise, set the node as a key. Node as set, rax set data will set is key. Increases the number of elements and returns 1 because an element was inserted, while 0 if element already exists. Okay, we want to do some of this because some of this work is not done here. So this is the get or put. So we say, but wait the problem. Wait a second. We can't know the old value though. But we can say this. We can do old value init of type t. It's of type T, the old value. That's fine. Okay, so all value set value. Okay, that seems good. So what does checking if this is key mean for us? It means that for us, maybe we can make a function for it. On a node, we can say we can ask to a node if it is key. Yeah, I know, but we can't do that stuff. We can't do either. That's the problem. But there is still value in this pattern. Like, even if you can't modify the original thing, but by the way, you can't modify key pointer because the key doesn't exist anywhere in our, like, as one thing. It doesn't exist because it gets split across multiple nodes. The value pointer is going to be there mostly, but not always, because we want to avoid storing data in case that the value is null. So, so we can't give you a value pointer because there's not always going to be a value pointer. And so that's why we have to use a different API. And that's how it has to be. There's nothing else we can do. Unless we decide to drop the null optimization. But it seems good for me to have. So I'm going to try to keep it. So how do we know if a node is key? A node is key if is null. But we need to be careful because its null could be void. And then if value length is 1. So if value len is 1, then return true. If and is null type equals bool return and dot is null. Otherwise, return false. There you go. But maybe we can do it like this. We can return if is null. Otherwise, we return value of len equals 1. There you go. Simplified. Okay, so we have his key. So if h dot is key, then we return found existing equals true dot n equals h, and then what else? Old value. Actually, it doesn't have to be old value. It can just be value, and there's no reason for it to be like this. Do just value. So and then value is gonna be what? I guess it depends on is null, right? Is null type. In the case of bool, you know what? We need a Boolean version of this because this fucking check is annoying. I think. Let's do it like this. If null type is bool and h dot is null, return null, else return what? H dot value dot slice at 0. Like this. Okay, so this is the case where it is key. If it is not key, then we basically need to make it a key. But we don't do it here. We do it only in the other one. So here we do nothing, or rather, if it's not key, then we return basically the rest. Now that I think about it, is this? Yeah, I believe that this case is basically just doing this and then delaying some work here to make everything compatible. So what would this look like? So let's do the work here to make it work. This means that, so if the value is null, so if there are no nulls, then we need to add memory basically. We need to add memory. By the way, these are obviously like to-dos. So somehow we add memory and then we should be able to do this. N dot dot value dot init. I think we have init on value. And then we can say value. So this is basically how it works. Here we need to try to add memory. This is basically it. Yeah. And this should be probably implemented like this, like n.resize. And in n.resize, we pass down GPA. So interestingly, get or put doesn't need a GPA at all. Or actually does it? Wait a second. Fuck. I don't think we can implement this as a get or put at all, now that I think about it. You know why? Because once once you're trying to insert something, you have to commit. Because now that I think about it, as we run down the tree, what I've done up until now is the simple case where we basically everything matches and there's like no extra work to do, and we get immediately to the end. But guess what? If this does not happen, if at some point we need to mess around with the tree, well, we have messed around with the tree. Inserting the key is you have to commit at that point. There's nothing you can do. So it can't really be get or put as we're used here. Although, let me think about it for a moment. Do we commit also in that case? Get or put. Yes, wait, never mind. I take it back because we actually commit also in other APIs that have a get or put in Zig, because we set the value to like the value is at that point available in the collection. It's just set to undefined, so it's for you to set it. Yeah. So yeah, no, I take this back. There's no problem with this. Yeah. It's basically not a resize GPA, and then we say in here we say dot value equals 1. So we resize value, and then we write in it the value. Do we still have init? Yeah, we do. So this is try and dot actually it's gop.n. With this, we should resize the values equal set to 0, basically. Okay. Right, and another problem here that we need to keep in mind is that that is not enough, because we need to also have around the parent link. Because if we need to realloc, then we need to also do the parent link. So parent link is a pointer to node, and we probably need to pass this down to resize. Yeah. Something like this. This is gop dot parent link. Yeah, this should be something like this. We set value to 0, and this other one we set value to 1. Um, okay. Okay, so this case is handled. I think that we might implement what's missing and then just make it happen at this point, because low walk is implemented and this case is fully implemented. So as long as we basically, the idea is if we try to no, we can't make this work right away because this is the case where we match everything. So, well, in order to match everything, we need nodes that already match everything. That's not going to be the starting point. Unless we try to insert the empty string. This will work with the empty string now that I think about it. I think that the empty string will work, won't it? Yeah. Okay, so we can test it. We can test it in that sense at least. So as for the resize function, yeah, we need to implement it. Although, is this really a node thing? This is not really a node thing, is it? Let me think. I think resize is something that we need to implement in Flex. I think this needs to be flex.resize. Flex.resize. Yeah. This needs to be flex.resize. Gop.n. This. And this should return a new pointer, I guess. I guess we can make it return a new pointer. And if it is new, then we do gop.parent link equals new. We probably should update also n. We should update n. And I take this back. This being old value is good. New value. Old value, new value. Yeah. The parent link dot star is new. But we can start with this. Yeah, this works. This is how it has to be. And then we fix parent link on our end. Okay, so we need to implement flex resize. And to be honest, I think that for now we can just not do anything about it. Just for like making it a no-op, basically, just for the purpose of testing this. And it should work. So let's see our test. We make racks. Expect nodes equals 1, and then we do try r dot get or put. And we want nice. This gets solved by ZLS now. That's cool. GPA key is the empty string that gives us a GOP. GOP is this. And the answer is that found existing should be false. So try std testing dot expect gop dot found existing false. Or well, I guess we can negate this. Not found existing, that also works. Okay, let's see how are we faring with test. Except the void found bool 76. Haha, right. Right. Expected type flexible array found com time int 78. Oh, this is interesting. Right, because these guys are structs with .len inside. So actually, even if you want to, you cannot easily do this. Yeah, no, never mind. So this has to be no dot. Expected type root racks found const root racks. That is fair. We need to make this var. Type root racks get or put does not support initially struct initialization syntax. Type get or put does not support struct initialization syntax. The fuck is it supposed to be then? What? Oh, no, it's not a pointer. Value. Okay. Let's see. Expected IPU size found void 76, 75. Wait, what? Oh, this is in Zig Flex 75. Again, bro. Are you serious? Hmm. Fine. Let's do this. And I guess I can delete this at this point, hopefully. Extract the type usize found usize in flex root and flex 53. Yeah, and then what was this? 73. This is not true, man. Expected type usize found usize. This is absolutely not true. Items is wait, what is items? Yeah, it's many pointer. But if the field type then is void, then we return 30. What how the fuck do these two things go out of sync? What is going on? These two things cannot go out of sync. What is going on? Yeah. This is not field type. Yeah, that is indeed true. Wait a second. There is sus stuff. There is some sus stuff going on. Console log. Yeah. It's console log new. No, it's me completing Zig with JavaScript. So it's not field type. It's the type of land that is what we want to check. Although, wait, an alternative is. Wait, are we computing wrong then? Length type? So length type is what you pass in, and we have it. So in here, we should be able to say length type. If the name matches, we make this. And then if options.length type is void, then we return items. So this should match, but I already got a problem with this, which is why I changed it the first time. Like expected usize found void in 75. But that is not true. Because the whole point of what I'm doing is that this expression should not even be computed. Well, what if we do this? Although, no, I think, okay, I think I start to understand what the problem is. This is still not going to work. Yeah, the problem is that we are making this assessment. What if I do .len here? What happens if we do this? Commentating is not gonna help. Okay. This should work, man. This should really work. Maybe we can change this like this. What do you think of this? Still doesn't help us. Huh. Does this make it better, Zig? Are you happier now? Expected type slice weight found star flight weight 73. Expected slice weight found star weight. Why do you expect it to be a slice? When value lane is void, no, you do not expect a slice. What are you talking about? You know what we can do? We can switch on the return type. That maybe makes everything happier. Maybe that's what I should have done right away. Extended episode found void. Okay, so this is This is really not helping. Okay, let's try again. Expected type view size found void. Okay, this is like very painful, god damn it. We're making progress, but this is very, very painful. Okay, it seems that we got out of this. Expected type, type info, Roxana, blah, 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 found view size. Get or put, blah, 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 found view size. What? So we're back into route 133. What's happening here? Oh, yeah, right. What is this return? Type 64 is not indexable and not in range. Mainland. Oh no, what am I doing? What have I written? What? Yeah, what am I doing? Between bytes and um there you go. Expected type pointer found const pointer to various stuff. Oh. Do. If p-link parent link, blah blah blah. I guess this can be const. Is this it? This does not touch 3. No, what is going on? Expected type. Okay, let's take a look for a moment. So parent link right now is the place. So this points to a location that points to, it's a pointer to our node, right? Actually, you know what? Let's fix a type here just to be sure. It should be this. Is this correct? No. It's const. Okay, so yeah, okay, never mind. It actually was because of this. That makes sense. Function we don't void return type blah 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 implicitly returns. True. Because we haven't implemented stuff. Okay, nice. We got a index out of bounds. That actually makes sense because wait, that does not make sense. Wait a second. No, it does make sense. What is going on? Why can't we do this? Let's see. One 33. We're trying to return this, but no. Why is this happening? Is null type bool? Oh, right. The point is, wait a second. We might not. There might not be an old value. Okay, so this is not exactly like this. This is more like this. It's like an optional theme more than anything else. Although it can get confusing, can it? Because the problem is, okay, if found existing is false, then old value loses any meaning. In the past, we were able to in normal GOP, this is a pointer, so it always points to memory, and so whether the memory is initialized or not depends on the value of found existing, but it's fairly straightforward. In our case, since it's just a value, it's not about allocation in memory, then we have to decide what to put there when found existing is false, and that kind of sucks. Like this whole thing, it kind of sucks a little bit. And this is all for the is null optimization. I'm starting to have second thoughts about that optimization. To be perfectly honest, sure, it would be nice to not pay as much memory for nullables, but boy, does it fuck up the API. And that also means that we have to copy this. I guess it can be like this. But maybe this old value pointer, not found, null, or value, and we do this. So if there's a pointer, and then we do set value. So this means no found existing. Is saving that memory really that important? I do wonder, like, how often do you keep stuffing null in a Radix tree? Like, what is the point of stuffing null, a bunch of null values in the Radix tree? You know what I'm thinking? What I'm thinking is that this null optimization is probably useful for when somebody is trying to use a Radix tree as a set. But we don't need this because we can use void for that. You know what I'm thinking? I'm thinking we get completely rid of this null now that I think about it. I think that the C version has this dedicated feature because like the question is, let's say that the Radix tree doesn't have this feature, then what happens when you try to use it as a set? So you don't have values, you only have keys. What happens is that you have to provide values anyway, you have to provide pointers, and then those get stored and occupy a bunch of space that you don't need. So what you can do is pass null pointers as values, and then at that point you only pay one single bit. But we don't have to worry about this because what we will do is just use void as values. That said, though, that said, And that's actually entirely it. That's it. Yeah. Okay, so you know what? This is really telling me that we should just not do this. That said, how will the set case work for us? So what if the type that you pass in is void? Then and we basically want this to be a slice of voids. We want length type to be still a U1. We'll still use this way. Also, we could pass a bool here. That also could be something that we could support. In any case, so basically we flip this bit to say that something is a key. Yeah, is null gotta go. No more is null. No more len type. No more this. This is T. This is a U30. We don't care about this now. Yep. Oh man, this is going to simplify so many things. That said, the question of whether we should allocate space for probably or not, like the question still remains. So this is more like just this. Let's see. We call flex resize value 1. Hello, C3PO. And if we do resize, then this, and we do, and then we need also to do this, I would say. If T is different than void, or more like if size. Oh, you know what? I think that we can leave everything else and then it will automatically cancel out without us having to do anything. I think. Yep. This is the U30. Found existing if is key. PTR is slice at 0. Although it's more like this. We do this. That said, we are delaying the resize here, but we should not. We should not delay the resize at all. Yeah. Yeah, we make space for it. How can I say? I guess we can do this if it's not key here. How does it work? Because calling is key here, it's too late. So no, this should be this. There we go. If not found existing, then we resize GPA. We resize everything to make space for value. Okay, this seems good. This seems good. Okay, let's see how are we faring with programming errors. We have a bunch, huh? So we don't have set value anymore. We don't care about it. Because we don't care about this either. This can go back to being a dumb thingy. We do the resize here. We set h. We set the parent link here. So this should not be a problem. Then what is the next thing? Pointless discard of function parameter. We are discarding GPA somewhere. Oh, here. Okay. Next problem. What is it? Null and type U30. And yes, there is no resizing flex. So we basically would need to implement resizing flex. Create, destroy, and here resize. And so how does it work? You give me GPA. You give me the parent struct, which is an any type. And then you give me new lengths. Yeah. And to be honest, we can do this for now. Expected optional type found void. Good point. No filling n in store get output. Yeah. The here. Oh wait, it is here. It's in source root. What is it? 7. Oh yeah. Index out of bounds. Okay, we're making progress. Is this really an index out of bounds? It is. It is, and because here we're not doing shit, so I'm starting to think that actually this should be this, type, and then P should be a pointer to T, and this is what we return here. It's probably better. So we need to loop over all the lengths. I think we can even do better. Fields. Type of new lengths. At field P, comma, f.name equals at field new lengths f dot name. Okay, so this is hacky. We're basically updating lengths, but we're actually not reallocating shit. So this is whack. What I'm doing here is whack. But it should get us out of this index out of bound, which is correct. It's a correct index out of bound. That's expected for arguments found at 3. Right, because I changed the API. So node GPAH. Value type what must be completely known, but index value is runtime known. Inline 4. There you go. Expected type root flexible array use size. Oh shit, right. Yeah. .len. Nice. Yes, we got an invalid 3. That's correct. Basically, what's happening is that when we try to de-init, now we see that the numbers don't match and the allocator refuses to do the 3 because the length doesn't match what's expected. That is correct. And that is because our resize doesn't really resize. It just lies about it. So we should do that. But you know what? Under the assumption that there is nothing really important written in there in the tail, which is currently the case. Currently, the tail is completely meaningless for us. Then we can actually do this. So we can do try GPA dot resize. Resize. Yeah, what? I guess it's P. And then, but we're going to need to typecast P. Well, I'll pointer cast a bunch. The new length needs to be yeah, fuck. We basically need to count again the size of everything. Well, I mean, I guess it's fine. It's gonna be size of size of t plus, and I guess I can put it here in a loop, which is not a great idea, but it's probably gonna work like this. Size of t plus this. There you go. Extended module slicer reverse of type instead. Yeah. Oh, it actually needs to have a known length, doesn't it? Oh, this is interesting. So this is gonna be std mem dot bytes as slice. Given a slice of bytes returns a slice of the specified type. No. Guess this. Pointer cast p. And then this is gonna be resize bytes. Error. Wait, what? Expected or unit type found bool. Let's see what happened now. Integer overflow. Allocation. Alignment 4 does not match free. Alignment 1. Yeah, I don't know what this one is. I mean, it's just a matter of looking exactly what the heck is going on. But allocation with alignment 4 does not match free with alignment 1. Does not match free with alignment 1. So the allocation with alignment 4 is our pointer. But I guess this is it. Resize is, wait, resize is trying to free shit? No, it shouldn't. Resize should not be trying to free. Oh no, it does retry to free. If new len equals 0, then free. But new len should not be 0. New len is not going to be 0. So what the heck is going on here? Also, the stack trace is inside create. Alloc with options. And then it says allocation alignment 4 does not match free alignment 1. But we got it into init. Init got us into creating a node. And this made us fail here. Wait, why are we failing? Oh, Wait. No. Okay, this is showing us the allocation, and this is showing us the free. And the free inside resize is what's blowing up. Okay, this is it. So okay. So we're not doing too bad. So this thing is having trouble. Yeah. We can do this. Align something you ate. What is this? Align of T. There we go. Are you happy? Okay, now we're having another invalid free. Okay, so we're doing the math wrong probably. But this is good. By the way, we're doing the math wrong here probably because we don't have we're not accounting for padding for alignment of other things. So the problem is literally just that our math here is out of sync with our math elsewhere. And that's totally fair because here I was just trying to hack it and have like a quick and dirty way of doing it. But yeah, it's fine. It's definitely absolutely fine. So, also wait. Because we should resize to new land times the size of that field. In any case, there's basically a bunch of logic missing here. The problem is this: we have logic that should compute correctly what the new size should be. We're just not doing it, so we need to implement it. I have to go though because I have a meeting right now. So let me double check if my oh god. Okay, I don't have to go right away. I can say a bit more. Cool. Okay. Uh, Maybe we can try to get this to work for real, since I have more time. I think this is interesting because this is going to be a key part of our algorithm, and it's going to be annoying, man. So basically, the problem is this. So we cannot resize here. We need to do realloc, I think. Like the name should be realloc, not resize. Yeah. Okay, let's see. Okay, we need to understand what is the old size. And the problem is that we don't know what the old size is because we compute the size in create and destroy. But we don't have something to just query the size. And we should. At the end of the day, create should be it. Like this exact thing here, right? Like we can literally just make it a function. Yeah. Size of p type oh, I guess there's like type size. No, there's not type size. The fuck am I talking about? There's only runtime size. Although, wait, what am I using in here to do this? P info. Yeah. So, mm, yeah, no, here I'm using a provided length instead of reading. You know what? Let's take it easy with creating abstractions. Let's plop this back and let's make a different function. Pub function current size. Current size takes a p type p pointer to constant pointer to p, returns usize, service size of p, and then for p info, which is going to be this, we say p info fields for each field. If it's flexible, if it's not flexible, we continue. If it is flexible, then we do size plus equals aligning forward based on the field type. And then we add not this, but we add at field p, comma, field.name.len and return size. So this gives us the current size. Although this could be really renamed to size. Okay, so this is size. Oh no, now we can't use it elsewhere. Oh no, oh shit. I take it back. Current size for the outer function is fine then. Align 4 seconds per meter is still all the size. Oh yeah, thank you. Well, I reverted it, so we're good now. Okay, so this is only the current size, which I think we do somewhere, like in destroy. That's what we do, right? In actually, type info len type different than void. Yeah, Actually, yes. Current size requires us to do this. Oh, you know what? That code is absolutely wrong. Yeah. This code is wrong because it doesn't account for any training elements. So never mind. We need to copy this. This is the correct logic up until here. This is correct. Problem is, what do we do with void len? I guess we can do this. Okay. And then we return size. Okay. Now let's go back to here. In here we do flex resize. The problem with resize is that we don't know what the old trailing length was. And you will have to tell us necessarily, because it's not stored anywhere in an explicit manner. So yeah. Also, should resize manage what we have in there? So I guess resize needs another parameter, which is going to be void len is if h.layout is dot merge, then 1, else h.bytes.len. Yeah, you have to pass it in. Which makes me want to pass it here and leave the complicated argument last. There we go. So now resize here. So times GPA pointer t, then void len, usize. Actually, making it optional is kind of bad, but whatever. So void len and then new lengths, any type, and then okay, so put everything on a new line. So what are we doing here? Instead of, we need to compute the old length. So const old len is you know what? Even though I made a function that tells you what the current size is, in reality, it's not what I want to use in there, because in there I want to do all things at once. So I think I want this. Let's see. Okay, we are computing size. But as we compute the size, we say, sure, aligns forward, but then we say, okay, we found a field that has a length type non-void, so we sum that len, and then we also do this at the same time. if as field new lengths if it has that field, then we do size. Well, can we add it? Do we subtract it? We do minus. No, you know what? I'm dumb because we need to compute both old and new size at the same time. Yeah, and these are separate jobs because old size. Yeah, we can't do both at once. Old size is entirely us reading what's present, and then new size is basically looping over new lengths and in doing what actually? Well, if new length sends 5, then are we? What does it mean? It depends on the old stuff, right? So now maybe I take it back because as we are looping this stuff, maybe what we can also do is like old size and new size. So old size. So this is all old size calculation, but then there's also new size. And new size is not based on at all on what you have in here. No, it's not. It's not true that it's not based at all. It's based on the delta, right? So here instead new size is gonna be at field new lengths. It's gonna be new lengths minus sorry, field new lengths field dot name minus this guy. Does this make sense? So previously, like a given list had 5 elements in it, and the new length says that it needs to have 10, so we need to add 5. We need to do the new one minus the old one. Yeah. That says new size also needs alignment work happening, and we also need to worry about this. We also need to worry about this. Has field new length field dot name. Then we do new size is not the old field, but void len dot question mark. Sorry, no, the new stuff minus void len dot question mark. Okay. Okay, we're only missing, I think, alignment. So the idea is that a new size starts at the size of P for sure. And then we also need to do this. We need to align forward new size. Okay, so with this we have old size and new size. And now it's time. So let's see, realloc. This function requests a new byte size for an existing allocation, which can be larger, smaller, or the same size. If n is 0, this is the same as 3. If all mem may have a length 0, which makes this a new allocation, the function only fails without memory conditions, unlike remap, which returns null when allocator implementation cannot do the realloc more efficiently than the caller. And resize. You know what? I think it's remap that what we want exactly. Like for us, the correct operation is remap. Because the problem with realloc is that it will copy everything over, and that's not good for us. That's a bad copy, actually. So we don't want that. Here we want to use remap. Okay, let's use remap. Allocation is gonna be, oh, did I delete all that code? God damn it. Okay. Const bytes is pointer star align of p u8 equals pointer cast p, and then we want to remap, and then we okay, and then we want to remap bytes 0 dot dot old size to new size, and we're saying the remap in unknown return value indicates that the size was successful. The allocation may have the same address, may have been relocated. In either case, the allocation now has size new len. A non-return value indicates that the resize would be equivalent to allocating new memory, copying the bytes from the old memory and then freeing the old memory. In such case, more efficient for the caller to perform these operations. Yeah. So I guess it's like this. It's either an if or else. In the or else case, so we must fail do everything manually. New PTR equals, I guess, bytes we can do. Then return null, I guess. Okay, for now, let's do it like this. With one caveat that we're not setting these new values. We need also to set these new values on every field. Also, wait, am I doing this stuff in the loop? Oh no. This needs to be outside the for loop. And in the for loop, after we're done with the math, we need to do this. At field p, comma, field name of len equals Okay, let's see how far we get. Not much. Except our unit type found blah blah blah. Oh, remap doesn't return an error? Really? Incompatible types, slice of a line for U8 and void. True. There we go, unreachable. Reach unreachable code. God damn it. 228, the one inside here. Really? Remap? Okay, let me take a look. std debug.print. Old len, old size. Looks like a sus thing that we're being told. Old size 8, new size 4. No, that should not be the case. That should not be the case. Oh, right. There's the else case here that we're missing. New size needs to do field lane. Yeah. Still old size 8, new size 4. What? No, that should not be the case. Hmm. There is something not good happening here because, yeah, we align forward every time. We look at the land type. If it is not void, then we grab the value. We add it to old len because that which is correct. Then we look at if new length mentions it, and if it does, we grab that value. And we say the new size is this new value minus the old value. And then we set it. Otherwise, new size needs to be whatever the old thing was. Does that make sense? Let's see. Old size was 2, new size is 5. So if both are set, then new size is going to be 5 minus 2. No, fuck. What am I doing? That's the delta. New size needs to be whatever new line says, period. It doesn't matter what it said before. I always think of it as how many bytes it needs to grow, but no, this is the new total length, and that's why I was getting confused. Whole size 8, new size 4. Okay, the fact that his name doesn't change is scary. Why is that number now changing while I'm changing things? I'm changing the math. God damn it, man. I don't know. Plus 100. Please show me a 100. Show me a big number. Okay. 104. Oh god. Also, what is this? We're missing a plus. That's what's happening. There we go. Okay, so we add the new field land. Otherwise, we add the old field land. There we go. Old size 8, new size 12. Does that make sense? It does, because our thing is making space for a usize value, I believe. And that is... Wait, that is not 4 bytes. We're missing something. Oh yeah, we're not multiplying by the size of things. So when we're computing this stuff, the size is this. But then every time we do this, the old code was doing it fine, right? It's just me right now being silly because I kind of forgot how to program. Yeah, we were multiplying by the size of stuff. Should continue doing so. And that's actually exactly what I need to do. It's this. So we start with this. We align forward. Then it's fill length times the size of its child. And same here. Time the size of its child. Field length times the size of its child. Yeah. Ah, there we go. Where are we tripping before 2010? Was this really it? No, it was here. Well, from new length, we don't have to worry because those numbers are going to be what? Okay. There we go. Now we're cooking. There we go. Although old size being 8 is still a lot, but that makes sense. That must be padding. But going to 16 is correct. Yes. When we're reaching unreachable in resize, really, why is resize being so weak? Resize refuses to do what it should do. That's disappointing. Okay, so how does it work? Remap fail, do everything manually. Yeah, so how do we do everything manually? It works like this. Const copy equals of type p equals p dot star. We copy the old data in the header. Actually, does it even make sense? No, it doesn't even make sense. We don't care about that. So what we want to do is, although we actually do want to do this before here. We actually do want to do that. But we're not going to worry about it now. So what's happening is the allocation may have the same address or may have been reallocated. In either case, the allocation now has a size of new len. A null return value indicates that the size would be equivalent to allocating new memory, copying bytes from the old memory, and then freeing the old memory. But how can an allocator do that more efficiently, but also change the pointer? When does that happen? And in any case, we are remapping. We copy now. So sorry, we I guess make a new one. So we do const new equals try GPA dot actually what are we calling GPA? Might as well call flex at that point, no? Try flex dot create. And this is still us actually. Create P GPA and then what is lengths? Haha. Doesn't the music distract you? No, it does not. Here's the funny thing. This interface, while it looks cool, it doesn't work for us in this case because we can't do length. So never mind. Create is not the correct interface. We want GPA. And GPA.create, GPA.unlock with options, which is what we already do here. We want this. So let's see. Unlock with options, new size, alignment of P. This is last thing. Optional sentinel, no sentinel. This is going to be our data. Then this is new. We pointer cast it to P. And then we do new dot star equals copy, the old copy. And then technically we should rewrite other stuff. So there's like a to do here. We need to rewrite the tails, but we're not doing it. And so we return basically new. Let's see how this goes. Allocation size 16 bytes does not match free size 12. Uh-oh. So this is 234. This is the allocation that we just made. And then when we try to free it, we think it has a different size. Because somewhere we think that it's 12 instead of 16. And I bet you that this has entirely to do with the fact that we are not multiplying by size of in when we need to in destroy. Destroy, we look at size, starts here. We do aligns forward. We do this, but we don't multiply in here. as well. We need to multiply, of course. Now let's see if things get better. Yuan cannot. Okay, I see what's happening. We are leaking. Yes, we are leaking. Why are we leaking? Because we need to free the old one when we make a new one. So here we make a new one. And then we need to do GPA.free bytes. Expected type line 48 does not support field access. Slice.len. Oh, right. 0 dot all size. There we go. And now, and our test succeeds. So we have implemented some of the code. There's still a bunch of stuff that we're not dealing with. But yeah, this for now works well enough that we can get or put one item in it. And we can say that it's not found anything existing. Then we can do this. So we have a gop on hand, so we can do gop dot value ptr dot star equals 42. And then we can try to gop again. We can try a second gop. And this time we expect to have found existing, and we expect this to be also. So try std testing.expect equal 42, comma, this guy. We'll pass this. We pass. So yeah, we were able to successfully write something and take it out. There are there's a ton of stuff missing, obviously, but we made progress. We've implemented some of resize, which yeah, it's fine. I'm weirded out by remap though. I'm like truly weirded out by it. Why is it efficient for it to change a pointer? I don't get it. But oh no, I do get it. Actually, it's in the name. It's remap. It's virtual memory shenanigans. So the answer is that I think I get it. The answer is that remap is literally entirely leveraging virtual memory stuff. So you probably have an allocation in one page, but there's some other stuff in the same page. So what remap can do is, or you know what? No, never mind. There's a page. Then you want to grow to a second page, but the page right after is already occupied. So what it can do is take the current memory page, just remap it somewhere else in the address space where there's some space afterwards. And so it hasn't moved a single byte. It just has moved around page mapping. And now there's free space in front of it, and the remap can succeed. The data, it has not moved any data from memory, but there's a new pointer now. I get it now. Now I get it. Okay. So we need to implement these things, I guess. Okay. I think I'm good. I think this is a good place where to stop. So I'm gonna call it today. Thank you for hanging out. We we got the Radix tree to do some basic stuff. So I guess next time what we will want to do is is continue down here and implement the remaining algorithms. Oh no, there's an label. So we need to implement the remaining algorithms for insertion. And once we're done with this, which in any case is still some work, but once we're done with this, we actually have gained a lot more functionality because we'll be able to add anything that we want to the tree, and we will be able to test that. So that's cool. So far, this abstraction is working. It's not without flaws. It has, well, let's say that it has its moments, but I mean, if you look at it, the Rex code is not too bad. Really, it's not too bad. Okay, so with this, I'm gonna call it a day. So thank you all for hanging out. And is there anybody who I should raid? Anybody doing Zig? There's Lucas Develops. I'm gonna raid Lucas Develops. So go say hi and have a nice day.